the equations on the left are, in fact, the exact same things as the equations on the right. Now, why did I go about doing that? This is why. First of all, this one is in standard form, but this is in vertex form, and this one is in vertex form. And just a quick reminder, you remember that vertex form is ax minus h squared plus k, okay? Standard form is ax squared plus bx plus c, okay? So these are the two different forms. And it is really easy for you to find the discriminant when your equation is in standard form. If your equation is not in standard form, then you can still find the discriminant, but you're going to have to do the algebra and put it in standard form in order to figure out what the discriminant is. Please remember that A is the coefficient of the x squared term. That's this right here. B is the coefficient of the linear term. That would be this one. You're squaring that one, so that's always going to be positive right there. And then C is the constant, which goes right here. Write down the discriminant is b squared minus 4ac. I've done the math for you here, so that all you have to do is look at A is 1, B is 2, C is -8 for the red graph, okay? The hardest one is the green one. And the reason it is because the numbers are bigger. That's just, there's nothing else to it, but the numbers are bigger. So, okay, so B is -32, A is 2, and C is 131. Okay, so if I calculate the discriminant, it's going to be -32 squared, that's B squared, minus 4 times 2 times 131. -32 times -32, this is 1024, minus 8 times 131. 8 times 131. Well, 8 times 131 is 1048. Okay. So this over here is 1048. Okay. There's no tricks to this. Okay. There's absolutely no tricks to this. It is just that simple. You figure out what B squared is equal to. So then 1024 minus 1048 is that -24? Is that -24? Somebody who did it? Yes. Okay. Awesome. Thank you, Jared. -24. So, my red people, B squared, 2 squared, minus 4 times 1 times -8. Okay. Okay. So my red people, what did you guys get as your answer for the red? 4 minus a -32. So minus a negative is plus a positive. So this number right here, this discriminant is 36. Really not able to, okay. So B squared, that would be -16 times -16. That's B squared. This is B. Here's A is -1. C is -64. So B squared minus 4 times -1 times -64. 16 squared is 256. What is 4 times 64? -4 times -1 times -64 is -256. Perfect. So this turns out to be -256. See, actually what happens is this in parentheses turns out to be 256, and you end up with positive 256 minus 256, so you end up with a 0 down here. Okay, great. So 3 things can possibly happen: a positive discriminant, a negative discriminant, or a discriminant of 0. All right, what I have done here is I have taken the very first equation, which was the red, and plugged into quadratic formula. Okay, quadratic formula. And remember that back over here we had 36. Well, here's that 36 right here. Okay, so if we got a 36, we got a 0, and then we got a negative 24. Okay, these were the three things that we got. Well, if you will notice that the square root of 36 is simply 6. The square root of 36 is 6. And I ended up with 2 real roots. 2 real roots. Now, I want to show you what that looks like in a minute graphically. I did not calculate what happens with the negative, but I can tell you that this negative 24 ends up under the radical because the discriminant is just simply the radicand. It's whatever goes under that radical sign, okay? So if I were to end up with a negative under the radical sign, what would that mean? So if we end up with a negative discriminant, that simply means that we have 2 imaginary roots. And you are going to see this here in just a second because I'm going to graph each one of these 3 things and you're going to see them. If you have a discriminant that is 0, you have 1 real root. That's correct. Okay, so I want you to kind of keep this in the back of your mind, all right? Now, the reason why we ended up with such beautiful numbers right here was because 36 is a perfect square root, okay? So that was the reason why we ended up with beautiful roots down here. But if 36, if that number had not been a real pretty number like 36, let's say it had been 35 or 24 or 4, well, 4 is nice, but let's say it had been 10 or, 11, whatever. Any other number that was not a perfect square root, you would still get 2 real roots, but they would be irrational. Okay, so the reason why we got 2 really pretty answers down here was because this number right here was a perfect square root. Okay, so if it's positive, then you're going to have 2 real roots. If your discriminant is negative, you're going to have 2 imaginary roots. And if your discriminant is 0, you're going to have 1 root. Okay. This is what it looks like graphically. Okay. And these are the same red, blue, and green equations that I used on the very first page. For this red equation, what did we get for our discriminant? We got 36. For the blue equation, we got 0. And for the green equation, we got a discriminant of negative 24. Okay. And so we learned on the previous page that if your discriminant is positive, then there's going to be 2 real roots. If your discriminant is 0, there is 1 real root. And if your discriminant is negative, there are 2 imaginary roots. Now, some of you may not remember this, but a root is another word for x-intercept. There are some words that we mathematicians use interchangeably. Solutions. If I say find the solutions, if I say find the roots, find the x-intercepts, all of those things, those words we use interchangeably. So I want you to notice that in the red equation, it touched the x-axis, the parabola touched the x-axis 2 times. 2 times. We had a positive discriminant, and we have 2 real roots because it touched the x-axis twice. In the blue equation, we had a discriminant that was 0. And it only touches the x-axis 1 time. And where? On the vertex. Then over here in the green, where does that green parabola touch the x-axis? It doesn't. It doesn't touch the x-axis. That's why when we're trying to find the places where it touches the x-axis, we end up with imaginary numbers because it doesn't touch the x-axis. So we ended up with a negative discriminant, and that's why there are no real roots, but there are 2 imaginary roots. There are 3 things that could happen. If your discriminant is positive, it is going to touch 2 times. If your discriminant is negative, it is not going to touch at all. If your discriminant is 0, it is going to touch 1 time. And then I also put these up here just to prove to you that when the equation is in standard form, you still get the same graphs. Okay? The graphs are still the same. Right here, I could look at this parabola and tell you, oh, that parabola had a positive discriminant. This parabola had a negative discriminant, and this parabola had a discriminant that was 0.